the channel. Today we'll be looking at permutations and combinations. Quickly before I begin, I just want to say sorry I didn't upload quite recently. I was in a different country and so I couldn't really record. But now I'll be uploading again. So today we'll be looking at probably what's the hardest topic as considered by many people in math AA higher level, and it's one that you'll have to pay attention to. But luckily for you, it is quite a niche topic in math AA. So like at most you'll see a question or two on it, but it's still very, very important in understanding some of the other things that come later on. So basically, the base of this topic is factorials, and this is represented by an exclamation mark. And it's only defined for numbers n where n is greater than 0 or equal to 0, but that's a special case. But the actual function itself, we consider it defined for n greater than 0. So for instance, 7 has a factorial, but -7 does not. And yeah, that's pretty much it. And the factorial function just means you multiply every number up until that number. So for instance, for 3 factorial, you do 3 times 2 times 1. For 4 factorial, you do 4 times 3 times 2 times 1. And for 7 factorial, you do 7 times 6 times 5 times 4 times 3 times 2 times 1. So basically, n factorial means you do n times n minus 1 times n minus 2 all the way down to 2 and eventually 1. Now, we know that multiplying by 1 is not really necessary, so we can just leave it and say down to 2. But in the definition, we technically multiply by 1. As I said earlier, note that 0 factorial is 1, and there is a proof for it, but I highly doubt you'll ever need to know that proof during IB. So now let's look at permutations. So permutations are rearrangements of different objects where the order matters. So for example, if I have 4 letters A, B, C, D, and D, C, B, A, and A, C, B, D, these are all different ways of writing the same 4 letters A, B, C, D, right? And I'm sure you can see some other ways to write it that I didn't do. For example, you can write A, D, B, C, which is not written here. So permutations are basically just the ways you can rearrange objects where the order matters. So for instance, in the Olympics, whoever comes 5th, 6th, and 7th, those are 3 positions. And you can change who comes 5th, who comes 6th, and who comes 7th in many different ways. But whoever comes 5th probably wants to come 5th and not 7th, right? So the order there matters. They earned a 5th place position, so they have to be 5th place. And the person who came 7th has to be in 7th place, and the person who came 6th has to be in 6th place. So the order is quite important there. So that's basically why a permutation is important. And the way you do it is if you have n different objects, you can rearrange them in n factorial different ways. So, for instance, the sequence right up here, A, B, C, D, can be arranged in 4 factorial ways because we have A, we have B, we have C, and we have D. Now, you might be wondering, what sort of formula is this then? Because if it's just n factorial, what is this n minus r thingy down here? So, if from these 4 points, which can be arranged in 4 factorial ways, we only want to arrange 3 of them. Say we only want to arrange A, B, and C from A, B, C, D. In how many different ways can we change A, B, and C around and keep D constant and still get a sequence, a valid sequence? So in that case, we use this formula for permutation here. NPR equals n factorial divided by n minus r factorial. So if we take the entire sequence A, B, C, D as it is, then n minus r is equal to 0 because r here is A, B, C, D, so it's 4. N is 4, so we just have n factorial. So that's how you get this 4 factorial right here. But if we took only A, B, and C and ignore D, for instance, now we have n factorial divided by n minus 3 whole factorial because we've taken A, B, and C and we've ignored D. So r is actually equal to 3 here. So when we basically are ignoring stuff in a sequence or in like an order, in that case, we need an n minus r, where this r is always less than the total number uh, of elements in that sequence. So here r is 3 because we picked A, B, and C. I know this might sound complex right now, but I'll try and make it a bit simpler in the next two sort of slides. So essentially, all permutation combination questions that require something like this formula here can be broken down into two sections: grouping and anti-grouping, as I call them. So a grouping just means like two objects must be together. How many ways can you rearrange the letters of A, B, C, D, V such that D and V are always together, regardless of the order of D and V? So this is one type of permutation problem. So here we have a sequence A, B, C, D, V, and D and V need to be together. So basically it can either be ABC. We can start with DVABC, or we can have VDABC. Doesn't matter. But we can't have DABCV because D and V need to be together. So in this case, what we do is we say let x equals dv. So now we have a new sequence, abcx. And we know that when we're arranging four things, we have 4 factorial ways to arrange them. So to arrange abcx around, we need to arrange it in 4 factorial ways. And that's 4 times 3 times 2 times 1. So 24 ways to arrange abcx. And there are 2 factorial ways that we can arrange dv, because x is dv, right? So we can either have dv or we can have vd. And that's 2 factorial. So in order to find the number of ways to arrange a, b, c, d, v, we need to take the number of ways we can arrange a, b, c, x and multiply that with the number of ways that we can arrange dv. So that's 4 factorial times 2 factorial, which is 24 times 2, so that's 48. Here's a visual representation of something similar. So if we want to keep a group like this, we can do it in multiple different ways. So here you can group, this is a different example by the way, but you can group A, B, and B8 as together, considering them as distinct but keeping them together. You can do the same with BC and CB, and you can do the same with CD and DC in order to help with your calculations. So this is the grouping strategy. You just reassign a new variable to be the ones that are together, and then you find the number of ways you can arrange that new sequence and the number of ways you can arrange the internal sequence. So this. And now here's what's known as anti-grouping. This might seem a bit more complicated, but it's basically just basic subtraction, so it's not that hard. So this just means when 2 objects cannot be together. So like say you have 2 siblings, John and Josh, and they hate each other and they can't sit next to each other without fighting. So at the family Thanksgiving dinner, John has got to sit far away from Josh, so they can't be next to each other is the only condition the family has. So in how many ways can we do that? Well, when 2 objects can't be together, say A, B, C, D, V, and D and V can never be next to each other, then what we need to do first is find the number of ways they can sit together. So in my previous example, if it's a family of 5, A, B, C, D, and V, and D and V hate each other, we need to find the number of ways that we can sit D with V, which sounds counterintuitive, but that's how it works. So from the previous question, we know that there are 48 ways to arrange D and V together in this sequence. So for instance, DV can go at the front, DV can go in the middle, DV can go at the back, and so many more ways. But now, in order to make sure that we can keep D and V apart so that they don't fight at the Thanksgiving dinner and ruin Thanksgiving, we just need to find the total number of ways we can arrange A, B, C, D, and V, which is 5 factorial because there's 5 elements. So 1, 2, 3, 4, and 5. So the number of ways that D and V are apart from each other is actually equal to the total number of permutations, so 5 factorial, minus the number of permutations where they're next to each other, which is 48, as we calculated in the last slide, which gives us 5 factorial minus 48, which is actually equal to 72, because 5 factorial is actually just 120. So yeah, that's pretty much the only types of questions you'll get on permutations. So here's a quick trial that I'd like you to do. So pause the video and have a crack at it, and then I'll explain very soon how to do it. Alright, so now hopefully now that you've done the question, we'll have a look at it. So how many 3-digit passwords can you make out of the numbers 1 to 10? Well, the numbers 1 to 10 are basically 10 different numbers. So there's 1, 2, 3, 4, 5, blah, 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 up till 10. I'm sure you know how to count to 10, so yeah. And so 10 becomes our n right up here. So 10 is the total number of elements, and we're trying to make 3 digits codes. So we're trying to pick 3 numbers from 10. So we just put 10 at the numerator for n, and set r to 3. So this gives us 10 factorial divided by 10 minus 3 factorial, which is 10 factorial divided by 7 factorial. To simplify this, we just write this out. So we know 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, and 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we can see that this 7 times 6 times blah 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 is a common factor, so we just scratch them both off, leaving us with a 10 times 9 times 8, which comes out to 720. So now let's take a look at combinations. Combinations are very similar to permutations, but they're the case when the order does not matter. So for instance, you'd see this in the binomial theorem. So like when you're trying to expand x plus n to the 500 or something. In a permutation, the order always matters, but in a combination, it does not. So for instance, like I said here, Olympics medal winners would be a permutation because one wins gold, one wins silver, and one wins bronze. And you just listing the students in your class off the top of your head, it doesn't really matter what order they come in as long as you list them all, right? So that's a combination. You're just trying to make a list of people. The same sort of thing as with like a shopping list. It doesn't really matter whether you put corn first or milk first. As long as you get both corn and milk, you'll be kinda happy that you have it. So yeah, that's a combination. The combination, the order does not matter. The permutation, the order matters. So I've given you the answer to whether these two are permutations or combinations. Now I'll ask you one more. Is it a permutation or a combination when you try and pick all the red colored pencils out of your pencil case? So while you think about that, here's the formula for a combination. It's very similar to the formula for a permutation, which is right back here, except it has this r factorial term over here. So dividing by 1 over r factorial basically means that we account for the fact that the order does not matter. So it's just the permutation divided by the factorial of the number of things we select. So because we can arrange those things in r factorial ways, and that's factored into a permutation, to reverse the effect of that, we need to multiply by the reciprocal 1 over r factorial in order to get the number of combinations. So let's take a quick example. I think this topic is a little bit challenging to visualize, so the best way to do it is with examples. So in a class of 30, 12 people are left-handed. What is the probability of picking 16 right-handed individuals, assuming all of them have a preferred hand? So take a crack at this with this formula right over here, and I'll present the answer in a couple seconds. Alright, so now let's take a look at the answer. So in a class of 30, 12 people are left-handed, blah blah blah. What is the probability of picking 16 right-handed? So we know the number of right-handed people is 30 minus 12, because all have a preferred hand, and that means 18 people are right-handed. And if we choose any 16 from those from this entire class, we have 30 choose 16. So that is basically equal to 30 factorial divided by 16 factorial times 14 factorial, because that's 30 minus 16. And To get 16 right-handed students, we need to choose all of those right-handed students from the group of 18. So it's 18 choose 16. So again, that's 18 factorial divided by 16 factorial times 2 factorial, because 18 minus 16 is 2. So the probability of picking the number of right-handed people would just be the probability of picking 16 right-handed people divided by the probability of picking any 16 people. So that's 18 choose 16, because all of these are right-handed people, divided by the probability of picking any 16 people. So that gives us 0.000000105. So it basically tells us that it's almost impossible that we pick 16 right-handed people in this class. Maybe in a different class it's different, I don't know. So yeah, that's pretty much the end of this topic. Again, I'd like to reiterate that this is probably one of the hardest topics across the entire syllabus. So practicing questions like these is sort of the only way you can prepare for it. Um, but yeah, it gets quite important down the line, even though it's not really that important in its current form right now. So learning it quite well will really just help you get a better grade in math. So yeah, that's pretty much it. Thank you so much for watching, and I hope you found this video helpful. Please don't be discouraged if it seems confusing at first. Just try and stick with it, and eventually it will stick and you'll understand it. I hope you found it helpful, and see you next time.